Three more properties of logs to tack on. One of them, they both deal with having the same base and the same log. So if you have log base b of b to the a, the log stuff all cancels. This stuff cancels and you basically just get a. So like if we had log base 3 of 3 to the 9th, that would just become 9. And log base 2 of 2 to the x would just be x. And it's kind of annoying because you have three levels of text, of script. A subscript, a script, and a superscript, low, middle, high. And that can get confusing. That's part of why I like to use parentheses. Not all books and not all people do that. But the parentheses can kind of show what your main level of the function is. The reason this happens, I mean, think if you just had log base b of b to the a. We want to see what that equals. Suppose we don't know what this equals yet. We're trying to verify this property. Well, we know that to convert to exponential form, we'd do b to the something equals b to the a. Well, for that to work, for b to the something to equal b to the something must be a, so it's an a here. And that's where this property kind of comes from. It goes the direction also. If you're in exponential form, you would do b to the log base b of a equals a. It's like, we'll do examples first. So 6 to the log base 6 of 30 just equals 30. And 18 to the log base 18 of 9 equals 9. And 10 to the log base 10 of 7 equals 7. If the base of the log and the base of the exponent are the same, they essentially cancel each other. That's not really what happens, but it's a way to think about it. And again, if you wanted to think, if you want to know why this is the way it is, which I'm sure you do, I'm sure you're just dying to. Well, we want this to equal something, but we don't know what it equals. Well, right now it's in exponential form. To put it in log form, this would be the base. So I would say log base b of something, we don't really know what that would be, of something equals the exponent, and this is the exponent. Well, obviously this something has to be an a now to make these equal each other, so it equals a. But the best property of all is the all-powerful change of base formula. If we were in a class right now, you would see the skies open up, and a ray of light shine down, and angels in the background would be going, oh, because it's just so beautiful and so powerful. I'm even going to grab a creative pen here and give this thing some little sparkles just to show how wonderful it is. It lets you convert from any base to base 10. Really from any base to any other base. You can do any type of base you want, but it's most useful to do base 10. So if we wanted to find log base 2 of 12, this is really saying 2 to what power equals 12, which is a question we tried to answer before. Using the change of base formula, I can do log 12 divided by log 2. But this is now written in a base 10 fashion, and my calculator has a log of base 10 on it. Log of 12 divided by log of 2 is 3.58. So in 2 to the x equals 12, x is about equal to 3.58. If I do 2 to the 3.58, 2 to the previous answer, I get 12. I can actually use this to solve most of my exponential problems now. So if I had 7 to the x equals 200, I don't know what that is, so I convert to log form. Log base 7 of 200 equals x. I convert to log form. And then I do the change of base formula. Log 200 divided by log 7 equals x. Make sure you close your parentheses all the time. 2.72. So 2 to the 7 to the 2.72 comes out to 200. It's the change of base property, and it's just so awesome. And it really comes from a property we learned earlier. If you have, like, 3 to the x equals 10, well, I can take a log of both sides and pull the x out in front with that property of logs. And divide both sides by log 3. And I get log 10 divided by log 3 equals x. But that's really the same as just taking this right here and originally putting this into log form. So these two things are the same. And there's your change of base formula. It's beautiful. I hope you love it. I hope you have a great day.